All right, welcome. Today we are going to build from the ground up, probably the most fundamental building block in all of analog circuit design. We're talking about the CMOS common source amplifier, and we're going to do it starting right from the very beginning, from first principles. So, here's the plan. First, we'll tackle the why. The whole amplification challenge. Then we'll meet our star player, the MOSFET. After that, we'll get our hands dirty assembling the amplifier, analyze its gain, and then, super important, we'll look at some common traps you might fall into. And finally, we'll wrap it all up with a handy design toolkit. Let's get into it.
All right, first things first, the amplification challenge. You might be wondering, why do we even need to bother with amplifiers? Well, it's all about going from a whisper to a shout. See, the problem is, a lot of the signals we care about in the real world, they're just tiny.
Think about a microphone. The electrical signal it creates from your voice, it's minuscule. We're talking millivolts, maybe even microvolts. There is no way that tiny little voltage is going to power something beefy like a speaker.
So you've got this huge gap, right? On one side, you have the microphone with its tiny signal, and on the other, the speaker that needs a big one. We've got this missing link in the middle, and that is precisely the job of a voltage amplifier, to take that small input signal and create a much larger but still faithful copy of it.
So, what's our secret weapon for bridging this gap? Well, our building block is the mighty MOSFET transistor. At its heart, it's a voltage-controlled current source, and we're going to be looking at it specifically in the context of a technology called CMOS.
So what is this CMOS thing? It stands for complementary metal oxide semiconductor. And the key word there is complementary. It means we get to build two different types of transistors, N-type, or NMOS, and P-type, PMOS, on the very same chip. And trust me, that is a total game changer. It's the reason CMOS is the backbone of pretty much all modern electronics. It gives us, as designers, just incredible flexibility to build powerful and efficient circuits.
Okay, time to build. We're going to take our MOSFET and try to assemble a real working amplifier. Now, a little heads up, our first few attempts are going to fail. And that's totally on purpose, because understanding why the simple ideas don't work is actually the best way to understand what makes a good amplifier tick.
Okay, let's walk through this journey. Attempt 1, we just hook up a microphone, a MOSFET, and a resistor. What happens? Nothing. It fails because with no signal, the transistor's just sitting there, turned off. It can't amplify if it's not even on. So, attempt 2, let's add a DC battery at the input to turn it on. Good idea, right? Nope. Fails again. Why? Because there's no complete circuit, no path for that DC current to actually flow through. And that leads us to attempt 3. We add a second battery, our power supply, in the output loop. And success! We finally have a steady DC current, a bias current, and a complete path for it to flow. This is the key insight. An amplifier needs a stable DC condition to keep the transistor alive and kicking, ready to do its job.
And this working circuit, this little triumph of ours, it has a name. It's called the common source amplifier. The name is actually super descriptive. The input signal goes to the gate, the amplified output comes from the drain, and the source terminal, well, it's connected to a common point for both the input and the output. Hence, common source. Simple as that.
Okay, we build it. Now, the big question is, how good is it? How much does it actually amplify? To answer that, we need to analyze it. And here's where things get really interesting. To understand an amplifier, you have to think like you're living in two different worlds at the same time, the DC world and the AC world.
Let's break that down. The first world is large signal DC analysis. Think of this as setting the stage. It's the quiescent state. We look at the circuit with zero input signal, just the DC voltages to figure out the steady currents and voltages. This whole process, called biasing, is just to make sure the transistor is turned on and happy in the right operating region. Then there's the second world, small signal AC analysis. This is the main event. This is the action. Here we look at how the circuit reacts to our tiny little input signal. This is where we find the all-important voltage gain. So DC sets the stage, AC is the performance.
So after you go through all the math of that small signal analysis, and we'll spare you the nitty-gritty for now, you boil it all down to this one beautiful, elegant, and incredibly powerful equation. The voltage gain, AV, equals minus GM times RD.
Now this equation tells a story, so let's decode it. What's AV? That's our voltage gain, the whole reason we're here. It's just the ratio of how much the output changes for a given change in the input. Okay, what about that minus sign out front? That's super important. It tells us the amplifier is inverting. When the input signal goes up, the output signal actually goes down.
It's a 180-degree phase shift. Then we have GM. This is the magic number. It's the transconductance, and it basically represents the raw power of our MOSFET. It tells you how good the transistor is at turning that little input voltage wiggle into a big output current wiggle. And finally, RD, the drain resistor. Its job is simple but crucial. It takes that changing current from the MOSFET and, thanks to Ohm's law, turns it back into the amplified output voltage we see. So you see, every part has a job.
All right, knowing the theory is great. But when you actually start designing, it's really easy to fall into some common traps. So let's talk about a few pitfalls to help you start thinking like a real circuit designer.
Here's a question that gets a lot of people. You look at a MOSFET symbol on a schematic. You see the three terminals, gate, drain, and source. But which one is the source and which one is the drain? The little arrow on the symbol just tells you if it's an NMOS or a PMOS. It doesn't tell you which is which. So, how do you know?
Well, it's actually all about voltage. The function of the terminal is determined by its electrical potential. For an NMOS transistor, the rule is simple. The source is whichever of the two terminals is at the lower voltage. The drain is at the higher voltage. For a PMOS, it's the exact opposite. The source is the one at the higher potential. You have to look at the circuit's voltages, not just the drawing.
Okay, now for the golden rule. The absolute, non-negotiable, most important rule for making a MOSFET act as an amplifier. It must be biased in what's called the saturation region. If it's not, it stops behaving like a nice voltage-controlled current source and starts acting more like a crummy voltage-controlled resistor. You get no amplification. For an NMOS, the condition you always have to check is that the drain-to-source voltage, VDS, is greater than the gate-to-source voltage, VGS, minus the threshold voltage. Check this, always.
Okay, we've been on quite a journey. So let's pull all of this together and distill it down into your personal amplifier design toolkit, a straightforward process you can use every time.
Here it is, your 3-step roadmap for amplifier design. Step 1, select your topology. You have to choose the right circuit for the job. Today we learned the common source, which is a great start. Step 2, bias the transistors. This is that crucial DC analysis part. You choose your DC voltages and currents to make sure every single transistor is happily in the saturation region and has the GM you're looking for. Step 3, analyze the AC characteristics. Now you whip out your small signal model and calculate the performance metrics you care about, like our voltage gain equation AV equals negative GM RD. Pick a circuit, bias it correctly, then analyze its performance. That's the flow.
And there you have it. We've gone from a simple problem, a whisper needing to become a shout, all the way to building and analyzing our very first amplifier. So I'll leave you with one final question to think about. You now know the gain is AV equals negative GM RD. If you needed more amplification, more gain, what would you change? What are the trade-offs? Something to chew on. Thanks so much for joining me on this explainer.